Hello everyone, myself Kajal Kumari, PhD research scholar working with Professor Mayank Goswami at Divya Drashti Imaging Laboratory, Department of Physics, IIT Roorkee. First of all, allow me to thank the ICI NDE 2022 Organizing Committee and community to give me a chance to present the recent finding progress in the field of non-destructive imaging. This presentation is about do we really need to recalibrate the city system configurations for every experiment. Here is the outline of this presentation that we will discuss in the upcoming slides. So first we come at the introduction part. So computer tomography is a non-destructive technique that has been extensively used in the field of medical science, material science, industrial applications, and many more. This animation is a self-explanatory of working and methodology of computer tomography. The first question come in our mind when we before starting the city experiment is that what should I set the values of the city geometry parameters. Some people choose the city geometry parameters according to their own convenience, and some perform the multiple experiments to find out the optimal city geometry parameters. But we cannot perform the multiple experiments on spot to find out the optimal city geometry parameters, because in medical science it raises the patient's risk of exposure to radiations, and while in industrial field that time, memory consumptions, and the changing the distribution of object with the time disapprove the on-spot optimization of city geometry parameters. Some people calculate the fan beam angle according to the size of the diameter, but in industrial applications we have restrictions in, and which is also decided by the number of detectors. But in industrial applications there are restrictions in data collection times and constraint on city geometry parameters. So these restrictions changes the city geometry parameters for every experiment, and uh, and uh, and and number of detectors and size of the object changes every time. The motivation of this work is to show the dependency of the density distribution of same size objects on city geometry parameters using a simulation study and experimentally. This study shows why it is necessary to recalibrate the city geometry parameters for every single object. In this work, we have demonstrated that for an optimized city geometry, changing the number of detectors can degrade the city image quality. This changes requires recalibration of city geometry. There is a myth that the more number of rotations will give a better resolution of city image. But in this study, we have demonstrated that it is not always true. For a better resolution, an optimal value of number of rotations required. Here is the experimental details of this work. This is the experimental setup of gamma CT scanner. This experiment comprise a gamma radioactive source, which is cesium 137, and two heterogeneous objects and a gamma ray detector, which is sodium iodide scintillation detector. These are the schematic. This is the schematic diagram of phantoms that we used in our study. The phantom first is made up of perspex, iron, and aluminium, and the phantom 2 is made up of perspex and iron. In phantom first, the heterogeneity is present at op center, while in the phantom first, the heterogeneity is present at the center. We have chosen these phantoms of same size, but the heterogeneity is present at different locations. So for these two phantoms, we have obtained the optimal city geometry parameters using a simulation study, and then we have performed the experimental results to verify the simulated study. So here is the simulation results. This is the image of phantom first, and this is of phantom 2, and we have calculated the optimal geometries for both the phantoms. These are written here. So we have observed that we have obtained the different geometry parameters for both the phantoms. Then we have reconstructed simulated reconstructed then we have obtained the reconstructed image of these phantoms simulated. So this is at the optimal setting of phantom first, and this is at the optimal settings of phantom 2, and the same is for the phantom 2. To verify these results, we have performed the experimental results. So here is the experimental results. We have observed that the experimental there is a good agreement between the simulation result and the experimental results. At the optimal settings of phantom first, at the optimal settings of phantom 2, the reconstructed image of phantom first loses the information at here, but although it gives the informations about the heterogeneity. While for phantom second, it at the optimal geometry of phantom first, it gives very weird result. These results are in good agreement with simulated results. Although however, there is a huge difference can be seen in the reconstructed results of phantom 2. Then we have done demonstrated the influence of number of detectors on city geometry parameters. Here is the simulation results. What we have done at the optimal geometry of phantom first, we have changed the number of detectors from 9 to 8. In our previous study, we have taken the number of detectors 9. Now we have taken the number of detectors 8, and we obtained the optimal geometry. For when the detectors were 9, the optimal geometry was 16, and when we changed the detectors from 9 to 8, the optimal geometry remains same, except the number of rotations is changes from 16 to 17. So we have reconstructed the image of phantom first simulated, and here is the root mean square error at these settings. To verify these results, we have performed the experiment. Here is the experimental results. This experiment shows these experiment results shows that at this setting, it is unable to differentiate between the iron and aluminum material, while it gives a clearly informations about the heterogeneity present in the sample. Then we have demonstrated the influence of number of rotations on city geometry. The for 8 number of detectors, the optimal geometry was at the optimal geometry was 17 number of rotations and 7 and I guess 56 56 degree fan beam angle. So we changed fan beam. We remains the fan beam angle same, and changed the number of rotations 16, 17, and 18. We have seen that a minor change means the rotation number of rotation changed in one gives a huge difference in the reconstructed results. and this is at the 18 number of rotations. So these results shows that not always greater number of rotations gives the better resolution of the image quality. There should be an optimal value. So here is the conclusion of this study. This paper in this paper we have investigated the dependency of density distribution of same size objects and the number of detectors, number of rotations on city geometry, city system configuration. For a fixed number of detectors, this simulation study gives the opportunity for the user to calculate the optimal city geometry parameters that we can use for real life experiment. This study shows why it is so necessary to calibrate the city system configuration for every single object. For an optimized city geometry, the changes in the number of detectors can degrade the city image quality. This changes requires recalibration of city geometry. And this studies also demonstrate that it is not necessary that always a large number of rotation will give a better resolution of city image. For a better resolution, an optimal value of rotations required. This study can be done with using Monte Carlo or Gantt 4 tool, but these tools will take the same time as the real experiment. But the simulation study will take less time as compared to this. So this study is a general study that can be applied to ionizing and non-ionizing radiation based city systems. Thank you.